Good day all. Today, the team of Russell, Peter, Sam, and Ryan will be presenting their design project labeled Consensus-Based Traffic Management Network. This is a third-year undergraduate project presented through the University of Guelph with administrative advisory provided by Professor R. Doney, PhD, and Megan Grovers, B.Eng. First, Peter will introduce the problem and background information.
Thanks, Ryan. So let's start by getting into some relevant statistics. Did you know that according to the Canadian Automobile Association, in 2019, the average commute time in the GTA had risen to about 28 minutes? A number I think many of us would honestly just be surprised is so low, considering the fact that 55% of those GTA commuters were spending upwards of 60 minutes to get to work every day. Traffic congestion is something most drivers can relate to, right? Especially in large urban areas. While commute times are commonly voiced as the main concern surrounding congestion, it's however easy to note that these longer idling times contribute to more wasted resources and more pollutant compounds like nitrous oxides, sulfur oxides, and carbon oxides entering into our environment, especially important in these urban areas where neighborhoods are put very close to large highway corridors, like in Toronto, the 401. Of traffic congestion as a whole may be entirely too large for a design course like this one. It was our thinking that if we could narrow the scope to something more attainable, then we may be able to create an impactful design. We began with an assumption that we could categorize traffic events into two main groups, predictable and unpredictable events. For example, a concert or sports event could be a predictable event, while a collision or a weather event could be considered an unpredictable event. Under this assumption, we could see that users already had the ability to plan around those predictable events, whether they hear about it from a friend or see it in the weeks leading up to the event. But by their very nature, unpredictable events could cause far more disruption to the user's day. Consider you're taking your regular route home and happen upon a 15-minute delay for a lane closure. Some might say that apps like Waze and Google Maps already provide this information, but it's important to note that many of the reported events can be inaccurate or out of date. Thus, we decided we would like to design a solution for providing users with clean and accurate data for where these events had taken place so they could make better decisions about where they plan to take their route or how an algorithm could potentially do that for them. So we started by defining what the constraint should be for our design. First, we wanted to ensure that users were not distracted by having to use the system. This was to keep roads safe and ensure that the system itself wasn't causing any accidents of its own. Second, it was important to integrate the system with already in place traffic infrastructure and that it adhere to all relevant traffic laws laid out by, for our example, the Ontario government. Last, we wanted to make sure that this was publicly accessible. We want as many people to use the system as possible to allow for the most impact to commute times. So then we decided to establish a set of criteria to narrow down our options. Our aim was to minimize the mean travel time for urban commuters, minimize the environmental impact as much as possible by reducing those idle times I mentioned earlier, and finally, we wanted to minimize the need to purchase any additional sensors or physical plant to bring down the cost of implementation. This is important because many of the current solutions available to governments can cost upwards of $1 million just for initial investment. So next, I'll pass it off to Ryan, who'll give us a bit more in-depth info about our design process.
The design process for this project consisted of 5 parts. Part 1, researching the problem, specifically the common traffic patterns in urban areas, the standards, laws, and regulations for the roads and highways in those areas, the technological integration capabilities of the current infrastructure, and available technologies that can be leveraged in the space. Part 2, solutioning the problem, building out multiple designs for potential implementation. In this case, there were 3 potential solutions. 1, a control systems based solution. 2, an algorithmic based solution. And the last one, which was the chosen one, a blockchain based solution. Part 3, deciding on a solution. This is understanding the criteria that we've developed and applying weights based on the level each criteria is met, then translating these findings into a final decision, which was the blockchain solution. developing the solution. This consisted of modeling the architecture, calculations, and engineering requirements of the system. And finally, is assessing the performance of the system through looking at its function, risk, safety, economics, and life cycle. To organize our priorities during the design process, the team used a variety of tools. For group organization, Microsoft Teams was used to store important documents and as a task management board. Excel was used to create planning documents for project management, such as a Gantt chart, and Discord was used for general collaboration and team communications. To prepare the required documentation, the team leveraged LaTeX through an online collaborative service called Overleaf, while managing citations and literature using Mendeley, and PowerPoint for additional visualizations. The team used two programming languages, one, Python, for simulation and modeling, and two, JavaScript, for any additional networking components. For further development, the team prioritized and recommends open source tools to minimize costs. For data, publicly available datasets were found containing historical information regarding road usage and lists of car accidents with their respective locations. Next, Russell will be overviewing our blockchain solution.
It has been shown that existing publicly available traffic data can be unreliable, particularly services that offer real-time notifications such as Waze. Without any verification mechanisms in place, it is ill-advised to use such data in a traffic event database for future traffic planning and prediction. However, it has been shown that these community-based event reports may arrive faster than those coming from official government sources, such as traffic cameras and police, and may even cover events that would traditionally go unreported. A blockchain network provides a unique opportunity to build a publicly maintained platform which combines the speed and breadth of community reporting with the reliability of data from traditional government sources. We designed a proof-of-event-based system that provides inherent verification of real-time traffic events. It does this by reaching consensus through a combination of three network participants: the event, witnesses, and verifiers. This contrasts with the proof-of-work-based networks such as cryptocurrencies, which rely on users of the network solving increasingly complex hash problems to create and verify new blocks on the network. As seen in the figure on the right, our blockchain architecture houses the event-specific data such as event type, location, and time on leaf nodes for each event that occurs while the block is being hashed. These leaves are linked in series with one another via the branch node. The root node then points to the various branch nodes in the block, which is divided into groups by city, region, or area. This method allows versatility in the way the branches are allocated to scale better in larger areas such as Toronto or the GTA. This tree structure is housed within each block, which is linked to each of the previous blocks containing events all the way back to the original Genesis block. These local chains could then be linked to a global chain, allowing for the possibility of global integration. Even though the network is decentralized, the information contained in the distributed ledger is public, meaning any person or company could integrate the notifications or historical data into their own system. With a reliable source of real-time traffic data, drivers and navigation services can better route traffic to avoid these events and decrease the mean travel time. In our network, drivers can act as witnesses or verifiers via hands-free operation of their cell phone. In addition to user data entry, the gyroscopic sensors and accelerometer inside the user's mobile device could also be used to obtain more data about the flow of traffic, as well as act as a verifier. In order to select the most suitable verifier, not only does the distance from the event need to be considered, or the amount of time it takes from the message to get from sender to receiver, but also the reputation of the user as well. This is the basis for the weighted delay calculation. This new reputation score we define in the bottom right-hand figure sums the reputation of the past events, represented by zeta. with a weighting factor phi based on how far in the past it happened compared to the newest event. This method was chosen to consider the full history of events to determine a user's reputability, ensuring the emphasis is taken off making a single mistake. This reputability score is our mechanism for rewarding users for contributing to the network, which is different from other blockchain networks which use newly minted cryptocurrency as a reward. On occurrence of the accident or event, the following actions will be taken. First, accident vehicles broadcast event generation requests to witness vehicles. Witness vehicles receive the requests and confirm with the accident vehicles. Upon confirmation, both accident and witness vehicles submit their respective timestamp, sensor, and location information. A lead verifier will then be elected via an algorithm that considers location as well as reputation score based on previous events. The lead verifier then tallies the votes and, upon consensus, hashes a new block and a notification can then be broadcast. And now over to Sam with the design defense.
In order to justify our functionality, a decision matrix was used. It contains the criteria used to evaluate each of our proposed designs, which gave weightings to travel time, environmental impact, equipment usage, maintainability, adjustability, and cost. The blockchain solution ended up with the highest score when the weightings of the table were applied, and was found to be the most maintainable and cost-effective solution. As mentioned, one of the constraints was to not distract the driver. By integrating the solution into the GPS software, the event detection is as invasive as having a GPS in a vehicle. Since there is no external change to the environment, no new laws or regulations need to be implemented, and the roads stay the same as before. The blockchain solution provides minimal environmental impact, since it is software-based. No new physical materials are introduced in the implementation. Instead, it uses existing infrastructure such as cellular towers and smartphones. The solution has no notable negative social impacts, as driving with a smartphone or GPS is fairly commonplace in North America. The solution aims to lower commute times and as a result make people happier, since they do not have to deal with traffic. Or, in the worst case scenario, that they are at least aware when it will occur so that they can brace for it. Developing the solution avoids traditional manufacturing costs that physical solutions would have. Instead, the bulk of the cost is the cost of development and maintenance of the software. Due to the decentralized nature of a blockchain, there is little to no overhead cost in keeping the solution online, since no servers are required. The longevity of the solution is highly connected with the use of the solution, and backing by existing route mapping software, such as Google Maps, would allow for the software to remain online for a long period of time. There are risks and uncertainties that can be seen with this solution, but the worst case scenario with the network just leads us to where infrastructure currently is. There is no loss in having the implementation, only a gain. With that being said, I will group that not everyone has cellular data or uses their phone when they drive, and the events get ignored by the driver as part of the worst case scenario. If there are not enough vehicles on the road required to make the network function, then it is safe to say that there will not be traffic in the first place. Finally, adoption of technology may be slow. This one may be an issue if the technology is provided separately from existing GPS and route planning applications, but if it is built into an existing application, the application will simply require an update. I will now pass the torch to Ryan for our closing remarks.
In summary, to ease traffic congestion due to unpredicted events, the team is recommending the implementation of a blockchain solution to verify the existence of these events, and therefore providing more robust, real-time data for traffic routing. The benefits of this will include lower commute times, minimal impact on existing infrastructure, and minimal distraction to current drivers. Thank you all for listening to this presentation on a consensus-based traffic management network. We look forward to hearing from you and for potential collaboration in the future.